Okay, guys. Section 5.4, graphing square root functions. We talked a little bit yesterday when we filled out this little sheet about what square root functions look like, and we said that it starts at 0 and then it goes, kind of in an arch to the right side. Doesn't go back this direction because you can't plug negatives inside of a square root, okay? So that's kind of basically what we are looking at today. You're going to be talking about like the numbers inside of a square root function, like what they do to this thing, how they move it around, and then we're going to talk about some domain and range and how you graph these things. So, starting with the function, starts here, goes forever to the right side. They give you some information here, and I'm not going to emphasize this too much. We are going to talk about domain and range below, though. So these are called square root functions, but sometimes you'll hear me call them radical functions because this symbol right here is called a radical. Okay, so radical functions, square root functions mean the same thing. All right. Identify domain and range. We're gonna look at this guy and see what happens to him, and then we'll talk about domain and range, and it's very easy from there. So this +4. If you need to look back at your peach colored sheet, this is actually peach colored for you, not white. When we're looking at the +4 and it's inside of that square root bar, okay? So you're adding and you're inside the square root, okay? So kind of like, oh, this one, exactly. That's exactly like that one, okay? So what that's doing is that's translating this 4 units to the left, okay? So I'm going to write here left 4 units, okay? So basically what I'm thinking about is this graph, but it's going to the left 4 units, okay? So left 1, 2, 3, 4. He's going to start here and he's going to go like this. Instead of starting at 0, he's going to start there and go like this. All right, then the only thing that we have left to do is domain and range. Domain, range. Domain is your x's, range is your y's. So domain x is going left and right. We're looking left and right how far he's going, okay? He's starting here and he's going forever to the right side, okay? So basically what's happening is all of your x's are greater than or equal to 4, -4, I'm sorry, greater than or equal to -4, okay, because that's as far to the left as he's going, all right? He's starting here and he's going forever to the right, all right? The range is up and down, the values that are up and down. So here, he is going up forever and ever and ever and ever and ever, but he will not go down past this point, okay? This y coordinate right here is at 0, so he doesn't go any below 0 on the y-axis. So your y coordinates are greater than or equal to 0. And that's your domain and range. Okay, I know we've done domain and range before, but getting to that point, looking at the graph of this and getting to there, that's really all that you have to do. Okay, just graph the thing before and do your domain and range. Okay, transformations. We filled out this transformation sheet, so you should be A-OK, ready to go for transformations, but just looking at this, they say K is a vertical, up or down. That number that's added to the end there or subtracted will tell you whether you're going up or down. The number that's inside of here is left or right. Okay? And it's the opposite sign. Opposite sign, all right? So minus will mean you're going to the right, plus will actually mean you're going to the left. And then they have another number here that is your a vertical stretch or vertical compression. So that basically takes this arch thing here and it either makes him taller, like more so arched, or it makes him a little bit flatter, so he's really, really tiny curved. Okay, so that's what that vertical stretch will do. Okay. All right, so down here, they go ahead and they have us plug some numbers in. So let's go ahead and do that. When you're given this function, we're going to plug some of those things in. All right. When you plug numbers in, always use parentheses. Let's see if I can make this. There we go. You can kind of see it a little bit better. Okay, so parentheses 2 squared plus 1. All right, and you get 5 when you plug that in, okay? Now let's see if this is a handy dandy calculator. There we go. I can hit the back button and I can go ahead and I can delete this number and I can insert 3 and I get 10 and I can go back and I can delete and I can insert 4. I get 17 and back and insert 5 and I get 26, and I'm going to go ahead and do the rest of these just in my head because I can go faster. So this is 37, this is 50, and this is 65. Okay, each one of those squared, and then plus 1. All right, so 2 is at 5, 3 is at 10. I didn't give you very good numbers to plug in. Blah, that's ugly. I'm going to go back and let's do some other numbers. Let's do like -2, -1, 0, 1, and then we'll go through those also. Okay, so let's do -2 now. I'm going to add some numbers in there because that isn't giving me a very good graph. -2, that is at 5. -1 is at 2, 0 is at 1, 1 would be at 2, etc., etc. Okay, so -2 is at 5, -1 is at 2, 0 is at 1, 1 is at 2, and then he goes up and up and up from there. Okay, now this guy looks like a parabola. Why does he look like a parabola? Because we're talking about x squared, okay? And x squared, the plus 1 just moves him up 1. So we could have probably graphed that without doing this whole table, right? If you know these rules that are on this sheet, it makes it a whole lot easier, okay? So that's what we're going to do with this next function. We are going to bypass all of the yucky stuff, and we're going to just graph this thing, all right? So starting with the square root of x, because that's what's called the parent function. This guy's parent function was x squared. This guy's parent function is the square root. So we're dealing with a function that looks like this to start with. All right. The -3 is going to move, or the +3, excuse me, is going to move him to the left 3. The, let's see, 2 is going to vertically stretch him by 2. The negative is going to flip him over the x-axis, and then he's going to be down 1. Okay, so I'm going to do a bunch of little dotted lines in here with a bunch of different colors, and then at the end we'll get one really nice, pretty graph. Okay, so we're starting with this function right here, which starts at 0. Okay, and then if I move him to the right 3, 1, 2, 3, he's going to look something like that. That's what he's going to look like. If I vertically stretch him by 2, that's going to make him taller. Vertically stretched, that's what I want to have happen to me, you know, but I'm not going to grow any taller. Vertically stretched, he's going to be really, really nice and tall like this. Okay, vertically stretched by 2. If I flip him over the x-axis, that's this guy right here. So now he's going to go down this way instead. Okay, and then if I go down 1, he's going to start right here. And he's going to go down 1 like this. So that's my ending final one right here. Starts there at -1, and he's going to go down, 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 down. Okay, he's going to be kind of tall. So going through those steps, that was a lot faster, or it would be a lot faster than actually graphing the points. Okay, so we have this guy looks like this. All right, now, gosh dang it, and I did that wrong. X plus 3 should be to the left 3. Gosh darn it. So it should be to the left 3. All right. Sorry. This guy. Not this one. So we should have gone left 3 to start with because X plus 3 means left. Sorry. I'm human too. I make mistakes. All right. So dealing with this guy, we need to do domain and range. Okay. So domain and range. Domains are x's left and right, so he will continue going to the right forever and ever and ever and ever and ever, but he won't go any past this point. So on the x-axis, that's at -3. All of my x's are greater than or equal to -3. Okay. For the range, up and down, he's going to go down forever, but he's never going to go past this point, right? That's where he cuts off. So he's cutting off at -1. The y's are all greater than or equal to -1. Okay. Over here we've forgot domain and range. Okay, domain is your x's going left and right, so he'll shoot off to the right and he'll shoot off to the left forever and ever and ever. So we put all reals. The range though, up and down, he's stopping at this point and he's not going any below that. So all of my y values are greater than or equal to 1. Okay, so if any of that was too fast, go ahead and rewind the video. and slow that down a little bit. I'm going to go to the back side now, though. And this first story problem talks about guitars. So with guitars, your pitch depends on the length of a string and the tension of the strings. So like if your string is really tight, it's going to make your pitch really high. Or if your string is really long, it's going to make your pitch really low. So the longer the string is, the higher the tension needs to be in order to produce a desired pitch. So the two like offset each other, all right? I'm going to skip down to the equation. The pitch is represented by this equation here, okay? This is important because we're dealing with square root or radical functions, all right? They have gone and graphed this from 0 to 10 on the x-axis, from 0 to 10, okay? They went ahead and had us graph that in part A. We plugged in points. They did it for us. Plug those in. This is what the graph of it looks like, okay? And we are analyzing in part B how much tension is needed for a pitch that's 200 or over 200, okay? If I want this number to be over 200, 200 mark is right here. If I want my pitch to be higher than 200, it looks like it's crossing right about at 5. So my tension has to be greater than or equal to 5 kg. Does that make sense? This way here is above 200 when it's greater than 5. Okay, so that was just kind of a look at this square root function and see what conclusions you can draw from that. All right. Example 4, last one. Find the inverse of x squared. Okay, so this is taking us back a couple sections to like section 5.3 where we did inverses. So the 4 steps to inverse. Step number 1, f of x becomes y. Step number 2, x and y switch with each other. Step number 3, you solve for y. And step number 4, y changes back to the name of f inverse of x, which looks like f to the negative 1 power. Okay, so step number 1, f of x becomes y, so now I have y equals x squared. Okay, then the x and y switch with each other. X equals y squared. Okay, number 3, solve for y. So I want to get y by itself, so I need to get rid of this square. So to do that, we take the square root. Okay, so y squared at the square root of that is just going to give me y, and that's it. And this guy just stays the square root of x, but since we put the square root in there, we do plus and minus. All right. And then step number 4, I'm going to flip these two around. I don't like the y being on this side, so I'm going to flip the y to this side, but then I'm going to rename him as f inverse of x, and then this is plus and minus the square root of x. So this is my new function. If I went too fast, pause the video and finish writing that. So we have plus and minus the square root of x. Okay, the square root of x we know starts at 0 and it goes like this, right? Starts at 0, goes like that. I'm going to put some really nice exact values in here. 9 would be at 3, etc., etc. Okay. I'm going to do that. Yeah, rather than just kind of like randomly putting that in there, these do actually cross through really nice points. Like the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. So that's where he's crossing exactly if you want some exact points to put on there. All right. Now, that's the positive square root function. The negative square root actually goes back down and is the same this direction. I think we've graphed him before on a coordinate plane when we were doing inverses a couple sections ago. I'm going to put this guy as a dotted line because we're going to talk about him in just a second. Now let's graph the original one. The original one was just y equals x squared, which you know what that one looks like. He starts here and he's a parabola, he goes up and over. So if you want some exact points, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So it's basically like exactly the same as these were over here. 4, 2, when you do the inverse, switches to 2, 4, right? We did that the other day. 9, 3 changes to 3, 9, etc., etc. All right, so if I graph this guy, here's my parabola going this way, and I have the other side of this graph going this direction. Okay, now, The reason why I put these as dotted lines here is because of this thing, okay? X is greater than or equal to 0. So when they have us graph the x squared, they only want us to graph on the x-axis where x is greater than 0. X is our negative back over here on this side, so we're going to ignore that side of the parabola. And when we do that and find the inverse, we're only looking at the positive square root of x. Okay, so if we ignore this half of the parabola, we're really going to ignore this half of my square root function. So really, when I find the inverse, I only need the positive square root of x. Okay, so that's something that they kind of add in there every once in a while. Don't let that really confuse you a whole lot, but they'll sometimes do that. So back from inverses, when we have that really wonderful magical dotted line y equals x, this guy is just a reflection of the original guy over top of that line. Okay, if I turn my paper even to make that straight up and down, he's exactly perfectly across the line from that. All right, so this just kind of goes to show you that the reason why the square root equation exists is because it undoes this guy. If you have a square, you take a square root. So that's why square root functions are very important. And we've already done computations like that before where we're solving for x, so you take the square root. So there's that, and that's all I have for notes. On your homework, there's only one side. The others, there's no problems on the other side, so you only have, I think it's practice is what you're doing. Do all of those on that front side. Since there's no back. So do all of those. When you're graphing, you don't have to make tables. You can go ahead and just look at the transformations using this sheet if you want to. If you're the type of person who has to make a table, go ahead and make a table for the ones that you have to graph. But you should be able to do them this way, and it makes it a lot faster and a lot easier. Okay, there you go.